So, hello. Today I am going to deliver a lecture on the topic fields. In physics, the concept of field is related to some kind of interactions, especially like electric field, gravitational field, magnetic field. These are vector fields. There are some other fields also. They are scalar field like temperature, thermal field we can say. So what are fields? Actually fields are the regions in which an object, a physical property, a physical parameter experience an interaction. Alright, so today we'll deal with three different fields. One is electric field, other is gravitational field, and last one is magnetic field. Now what is electric field? So it is a region in which a point charge, a system of charges experience electrostatic force. So electric field is defined as that's important. What is this? I will explain it a little later. But right now, this is very important point if we define electric field. So electric field is the electrostatic force experienced by test charge. Now, Q naught tends to 0 means this charge is small enough that it is not distorting the field. Gravitational field in the same way. So actually in different books symbol is different. Here I will use the symbol E subscript G. So mostly gravitational field, the concept of gravitational field is not used, but it is very handy to deal some complicated gravitational potentials and gravitational fields and to calculate forces related to it. Now in the same way it is limit, so here it will be mass m naught tends to 0 and then F upon m naught. And for magnetic field we have Biot-Savart's law to define magnetic field related to a small, vanishingly small current element. So like this is a current element and we are interested to find magnetic field somewhere here. We'll use right hand thumb rule. Curl of finger goes in. There is dB. So this dB is equal to some constant and IDL sine theta upon r square. So you can see here this is dl, small current carrying element carrying I current, and this is how it is producing magnetic field. Okay. If we talk about a small point charge and we place this test charge in the vicinity of it, then due to electrostatic repulsion it will experience a force this way. So E due to point charge is going to be q naught by r square divided by q naught. So it is k q by r square. This is point charge, for point charge. All right, so next, in the same way, for gravitational field, Eg is equal to some constant k m naught upon r square divided by m naught. So it will be km upon r square. You can see the similarity between all these formulae. They are inverse square law, and they are either radially outward or radially inward. So here it is radially outward, radially inward. But in case of magnetic field, the scenario is slightly changed. It forms a curl. So that's a different idea. So I will talk about this later. But in a broader way, they look identical. So what is the advantage? The advantage is if we solve something for electrostatic field, then we can apply that concept with a slight modification for gravitational field, and in some cases we can relate it with magnetic field as well. So all right, so if we imagine the concept of field, so let us suppose there is a point charge and it is a vanishingly small charge. So it is not going to exert force on any other particle, but it is going to experience force on itself. All right. So if this is a point charge, and if we have a small test charge, and we place that test charge here, later on we have placed that test charge here, then here, then here, then here, then here, then here, here also. Now, intuitively, we know that positive repel each other. So, also here, there will be a repulsion. This point charge is going to repel this test charge. We know there is Newton's third law still applicable in this context also. So means this point charge, this test charge is also going to exert some force on this point charge, but as we have assumed that this is vanishingly small, so it is somehow we have fixed here, and this is not fixed, so it will move. Not this point charge, but this test charge will move. So which way it is going to move? Obviously, it will go this way all the way to infinity. This is how it is going to. Here also, if it is placed here, all the way to infinity. Same here, and so on and so forth. In fact, if there is, I mean, in front of a screen, somewhere here, we have placed that point charge, it is going to come outside. Here, it will go there. So, ultimately, it will take a form of 3D structure. So, this field is not 2D, but due to this point charge, there will be a 3D structure, a 3D, very complicated to draw on 2D screen, but you can imagine it. Okay, it's a kind of a sphere, and you just hammer some iron nails into it. So these nails are coming out in all direction. This is how the electric field due to this point positive charge will take place. And of course, they will go outward. The electric field lines show the direction of acceleration or direction of force experienced by test charge placed in that region. In the same way, if we consider um, if we consider a negative point charge, then obviously then obviously see, now if I place a point test charge somewhere here, it will directly get attracted. We will get not much information. But if I have placed a test charge somewhere at the infinity, it will be attracted toward this negative charge all the way to its surface. Same here, same here, same here, same here, and so on and so forth. Here it is. And it is again spherically symmetric and radially inward. And if we discuss something about the mass, point mass, then same thing will happen. Here in electrostatic, there is attraction, there is repulsion, but in gravitation, there is only attraction. So if I place some point masses somewhere here, they are at infinity, so they will be get attracted toward this point mass all the way to its surface. So for in case of gravitation, there's always the gravitational field line starting from infinite till that massive object.